Now, in the previous lecture we gave some definitions of norm of a matrix. Let us just illustrate it through an example of what we mean by those norms and what is the measure that we are talking of a given matrix. Let us take a very simple example. Let us take this example of a simply a 2 by 2 matrix. Let us take this matrix 1 4 2 1. Now, the first norm that we have defined is the Euclidean norm. Which we denoted by f of a, and this definition was summation of absolute values of all the elements, square of that, then we take square root of this sum. Therefore, this will give us squares of all these elements 1 plus 16 plus 4 plus 1 to the power of half. So, that gives us root 22 as the measure if you take the Euclidean norm. Now, we have taken the maximum absolute row sum and maximum absolute column sum also as the norms. So, let us take those definitions. This is maximum absolute row sum. So, that means maximum of absolute row sum 1 plus 4, that is 5, 2 plus 1, that is 3. So, this is 5. Then we have given the maximum absolute column sum also as a measure. So, this is maximum absolute column sum, and that is maximum of this is 3, this is 5. So, this is 3 and 5, that is again equal to 5. Then the last definition that we have given as the Hilbert norm or the spectral norm, Hilbert norm, or we have also called this as spectral norm. Now, for this we have defined this, let us write down the definition of this. The definition of this was square root of spectral radius of A star E. A star is the conjugate transpose of E, conjugate transpose of E. Now, in our case a matrix is not symmetric, therefore, we need to form this particular matrix, but here the matrix is real, therefore, conjugate is same as the given matrix. So, this will be simply A transpose. So, what we need therefore is A transpose A is required, that is 1 4 2 1 1 4 2 1 and this is 1 4 2 1. This is transpose is 1 4 and 2 1. Therefore, this product is 1 plus 4, that is equal to 5, this is 4 plus 2, that is 6, 4 plus 2 6, 16 plus 1 17. Now, I need the spectral radius, that is the largest eigenvalue in magnitude of this matrix. So, I find the eigenvalues of this. Let us call this as B. So, that I have B minus lambda I, B minus lambda I, that is equal to 5 minus lambda 6, 6 17 minus lambda, determinant is equal to 0. I can expand this and write this as 5 minus lambda into 17 minus lambda minus 36 is 0. I simplify, lambda square minus 22 lambda plus this is 85 minus 36 is 0, which is same as lambda square minus 22 lambda plus 49 is equal to 0. Now, I can find the roots of this quadratic, straightforward. I will give the values of this. This is 19.5 and 2.5. So, that in this case the spectral norm is 19.5. Now, if the given matrix is symmetric, if the given matrix is symmetric, for example in this case, then maximum absolute row sum and maximum absolute column sum will be identical, because it is symmetric matrix. Furthermore, we mentioned that if it is symmetric, then the A transpose is equal to A. Therefore, we have shown that this will be simply equal to the spectral radius of the given matrix itself. So, if A is equal to A star, that is A is A transpose, if it is real, then this is the square of the eigenvalue, therefore under root will be this. Therefore, if I take a symmetric matrix, then everything will get simplified. For example, let us take another example like the matrix, say let us take 1 2 2 1. Now, if I take this matrix 1 2 2 1, let us find out what is our norm of A 2, that is Hilbert norm. Hilbert norm will be simply the spectral radius of A, because A is symmetric, because A is symmetric. Therefore, I need only the eigenvalues of A. So, I can find out A minus lambda I, determinant of it. So, I can find 1 minus lambda 2, 1 minus lambda is equal to 0, which gives me 1 minus lambda whole squared minus 4 is 0. We can take 4 to the right hand side and write 1 minus lambda is equal to plus minus 2, or lambda is 1 minus plus 2, that is minus 1 and 3. The largest eigenvalue in magnitude is 3, therefore, spectral radius of A is equal to 3, and in this case this is also equal to the spectral norm of the matrix. Therefore, the oh no, sorry, this is, there is no under root. Okay, let us keep it, retain it and then put spectral radius of A. Therefore, spectral radius of A is equal to 3, that is equal to norm of A2. Now, we are talking of the eigenvalues of a matrix, norm of a matrix. There must be some relation between the norm of a matrix and the eigenvalues of the corresponding matrix, and we have one result in which it says that the norm of a matrix is always greater than or equal to spectral radius of a matrix. Now, the equality we have seen the particular case in this example right here. When the matrix is symmetric, real symmetric, the spectral norm is equal to spectral radius of A. This norm is equal to spectral radius of A. So, the equality will be in that particular case. But the proof for this is just one line answer from the definition of a eigenvalue of a matrix. So, if I write down Ax is equal to lambda x, the definition of an eigenvalue problem, I take norm on both sides. So, I will write down norm of Ax is equal to norm of lambda x. Lambda is a number which is real or complex, therefore, it comes out as magnitude of lambda. So, I will first write the right hand side. So, that is magnitude of lambda norm of x. The norm of a product, norm of A into x is less than or equal to norm of A into norm of x. This will be less than or equal to norm of A into norm of x. Norm of a matrix or a vector is a non-zero positive quantity, therefore, norm of x can be cancelled on both sides. Therefore, we have magnitude of lambda is less than norm of A. This result is true for all eigenvalues of A. Therefore, we have the given result, that is norm of A is greater than or equal to spectral radius of A. So, just reverse this. This is true for all lambda, therefore, it is true for spectral radius. Therefore, norm of A is greater than or equal to spectral radius of A. Therefore, the norm gives the upper bound for the eigenvalues. Now, we need one more definition. What we have here is a sequence of powers of a matrix, a square, a cube, so on. We have a to the power of m. We would like to know when will this matrix, this sequence converges and converges to a null matrix. So I want to know the conditions under which limit m tending to infinity a to the power of m is a null matrix. Now I would like to show that this is true if norm of A is less than 1, or if and only if spectral radius of A is less than 1. Now the proof of this is just one line, because we let us take that it is norm of A is less than 1. Norm of A is less than 1. Then norm of a to the power of n is norm of, I will write down a into a, so on into a. Let us write down this m times norm. Then I will use the result norm of a into b is less than or equal to norm of a into norm of b. So this will be norm of a into norm of a into norm of a m times. So this will be norm of a to the power of m. Less than or equal to norm of a to the power of m. Now let us take limit. Limit of m tending to infinity a to the power of m, norm of this. Now apply the limit here. Limit, we take it out. So limit of m tending to infinity, norm of a less than or equal to m. Now norm of a is given as less than 1. Therefore norm a to the power of m, m tending to infinity will tend to a null matrix. Therefore the required condition is that norm of a should be less than 1, and because of the reason that norm of a is greater than or equal to spectral radius of a, we will have the condition that it's only if condition, only if I leave it, we need strictly less than 1. Spectral radius is less than 1. So norm of a less than 1, norm of a is greater than or equal to n. So we have spectral radius is less than or equal to norm of a less than 1. So that's what the result we have. Now but here we strictly require norm of spectral radius of a less than 1. Then it would always converge to a null matrix.
Sir, this shows that norm goes to 0, not matrix goes to 0.
You see, if the norm goes to 0, its measure is going to 0. Let us take any definition of a norm. Let us take the definition of, for example, Euclidean norm. Now this norm should go to 0, irrespective of all the components. Therefore the only possibility is that each one of these components should go to 0. Now if we take absolute row sum, absolute column sum, even if any one of the element is stationary or it is not changing, but all other elements are going to 0, then the maximum absolute row sum is going to be a finite constant. Therefore if the norm is to go to 0, every element should tend to 0. That means it would finally imply that the matrix A itself should go as a null matrix. Now this result we shall use for the what we finally need. So result 3 we can say, I got this infinite series I plus a square plus so. Now I would like to show that this converges if limit of m tend to infinity a to the power of m is null, and secondly it converges to I minus a inverse. You may think this is very similar to the binomial series. This is if you have a binomial series 1 plus x square so on, we know that it converges if magnitude of x is less than 1, and it will converge to 1 minus x to the power of minus 1 or 1 upon 1 minus x. So it's a result very similar to that that result holds if limit of a to the power of m is null. Now let us prove this. This is just one line. So let us take, if this is true, if limit m tending to infinity a to the power of m is null, then from the previous result spectral radius of A is less than 1. We have just shown that spectral radius is less than 1. That means there is no eigenvalue which is equal to 1. Largest eigenvalue in magnitude is less than 1. Therefore, there is no eigenvalue which is equal to 1 in magnitude. Therefore, there is no eigenvalue whose magnitude is equal to 1. This would imply that A minus I determinant is not equal to 0. I set lambda is equal to 1. A minus lambda I. So set lambda is equal to 1. So A minus I. But lambda is equal to 1 is not an eigenvalue. Therefore, the determinant of A minus I is not equal to 0. What does this imply? It implies I minus A inverse exists. If a matrix is non-singular, determinant of B is not equal to 0, its inverse exists. Therefore, we are showing that I minus A inverse exists. Therefore, under the condition, given condition, limit m tend to infinity a to the power of m is null, I minus A inverse always exists. That's what first we are showing. Now we will show that this result. What I do is I will take this equality. I will just multiply these two terms. I will take this as a to the power of m into I minus A. Let us just multiply it out. This I into I, that I have I. This is I into minus A plus A into I. That is minus A plus A cancels. Similarly, minus A square plus A square cancels, except the last term a to the power of m plus 1. Minus a to the power of m plus 1 is the only surviving element. Now what I do, since I minus A inverse exists, I post multiply by IA inverse. So I will have post multiply by I minus A inverse. Then this will simply read I plus A square plus A to the power of m is equal to I minus A m plus 1 I minus A inverse. Now let m tend to infinity. Let m tend to infinity. Now if m tends to infinity, a to the power of, we have taken a to the power of m tends to 0, therefore this tends to 0, this goes to infinity, and right hand side is I minus A inverse. Therefore we have the required result, I minus A inverse is equal to I plus A square plus so on. Therefore, the only condition for convergence of the right hand side is norm of A is less than 1 or spectral radius is strictly less than 1, then this sequence, then this infinite series converges always. Now let us use this for proving our convergence of our iterative methods. Now let's take this as a result or a theorem. Now the iteration method that we have derived for the successive relaxation, Gauss-Jacobi and Gauss-Seidel. For all of them, the iteration method, we have written it as xk plus 1 is equal to hxk plus c for Ax is equal to b, converges to the exact solution x is equal to A inverse b for any initial vector if norm of H is less than 1, or if and only if spectral radius of H is less than 1. In some of the examples that we have done earlier, using the Gauss-Jacobi and Gauss-Seidel methods, we have determined the iteration matrix H. And once I pick up this, what is this iteration matrix, I can find its norm or go to the spectral norm, I can find the eigenvalues, find the largest eigenvalue of that matrix and then see whether the largest eigenvalue is less than 1 in magnitude or not. One important thing here is we said it for any initial vector. So, arbitrary initial vector. So, if nothing is available for us, we can start with a 0. So, let the solution be 0, we can start with the solution also as 0 and even then it is going to converge. Now, let us prove this result in just few lines. Let us put k is equal to 0, 1, 2 onwards. So, let us take x 0 is equal to 0 for any initial vector. So, let us take 0 as initial vector. Then x 1 will be equal to 0 plus c, that is equal to c. I am substituting x 0 is equal to 0. So, I will put get here as c. Let us write down x 2. X 2 is equal to h x 1 plus c, but x 1 is equal to c, that is h c plus c, that is equal to h plus I into c. Now, we proceed further, x 3 is h x 2 plus c. So, h into this quantity. So, I will have h square plus h plus I of c. This is h into h square h and this is I coming from here and so on. If I take the k plus 1th iterate, this will become h to the power of k 1 less than this plus h to the power of k minus 1, so on, plus I c. Now, take limit, take k tending to infinity. So, the left hand side would be limit of k tending to infinity x k plus 1. Now, this result we have just now proved that this converges if norm of h is less than 1 or spectral radius is strictly less than 1. Therefore, this is equal to limit k tending to infinity h to the power of k minus 1 of c. This will be equal to I minus h inverse of c if norm of h is less than 1 or if and only if spectral radius of h is less than 1. Therefore, this is the convergence proof for all the iterative methods, that the iteration matrix will be obtained and we will find its norm or we will find its eigenvalues and find the spectral radius, and if the spectral radius is less than 1 then the iteration converges. If the spectral radius is greater than 1, it is sure it is going to diverge very fast. Let us take the Jacobi method. Now, h is minus d inverse of L plus u minus d inverse of L plus u, and this quantity that we have here, this limit, let us write down limit k tending to infinity x k plus 1 is I minus this, therefore, I plus D inverse of L plus U inverse of it into C. C was, I can write down C also here, C was D inverse of B, C was D inverse of B. Now, I will take D out from here. So, I will write down D inverse of D plus L plus U inverse. So, I have taken the common factor on the left. So, D inverse of D from here, L plus U inverse D inverse of B. This is equal to A, this is A, inverse of the product will be A inverse D inverse of inverse, that is D, and this is D inverse of B. Therefore, this is A inverse of B. Though the limit is indeed going to A inverse of B when we have this, the iteration matrix for H as Jacobi this, and the contribution of the right hand vector C is D inverse of B. So, this will always converge, and we have shown that will converge for any initial vector, arbitrary initial vector, and as I said, if nothing is available for you, you can start off with a 0. However, even if you know some values of the of this solution x1 x2 or any one of them, it will reduce few iterations. If you are starting at the 0 vector, the few more iterations will be taken for convergence, but if you know some approximate estimate, you can reduce the number of iterations for required convergence. Now, let us also see what would happen to Gauss-Seidel. Now, in the case of the Gauss-Seidel method, we have H is minus of D plus L inverse of U, and C was D plus L inverse of B. Therefore, let us repeat what we have done there, limit of k tending to infinity x k plus 1 is I minus H, that is I plus D plus L inverse of U D plus L inverse of B. Now, we do the same thing. Let me take out the factor D plus L inverse on the left, so that I is replaced by D plus L, D plus L inverse is I plus U inverse D plus L inverse of B. Now, again this is A. Therefore, I take the inverse of this product. So, I will have A inverse D plus L inverse of B, that is again A inverse B. Now, when once we have defined the convergence, that this is all these methods are going to converge provided the norm of the iteration matrix is less than 1 or spectral radius less than 1, we need to define how fast or give a measure of the rate of convergence. Now, we define the important number, that is the rate of convergence of any iterative method. Rate of convergence are usually referred as R of H, that is R for rate of convergence, H is the iteration matrix, that is defined as minus logarithm base 10 spectral radius of H. Some books do use base E also. So, you could but state that you are using base E. So, it is some of the books do use base E also. Now, you can see that spectral radius is a quantity less than 1, therefore, logarithm of that number is a negative number. So, this becomes a plus sign. Now, let us apply this, and then whatever we have done the examples earlier, let us see what is the rate of convergence methods that we have done there. The one example that we have done, I will just take the example show you to, but I will write it again. If you remember, we have solved this particular example using the Gauss-Jacobi Gauss-Seidel, and we also said perform 3 iterations and obtain the iteration matrices. So, we have done this example in which we obtain the iteration matrices for Gauss-Jacobi and Gauss-Seidel. So, based on this I will pick up the iteration matrix from here, but let us write down an example based on this. I will take this as find the rate of convergence of the Gauss-Seidel method applied to the system I will take this as 4 x 1 plus x 2 plus x 3 is equal to 2, x 1 plus 5 x 2 plus 2 x 3 is minus 6, x 1 plus 2 x 2 3 x 3 is equal to minus 4. Now, for this matrix, if you just look back your notes, we have derived this particular iteration matrix for Gauss-Seidel method, and we have obtained minus d inverse of L plus u and then multiplied out it and got this as the iteration matrix there. So, let us pick up this iteration matrix and use it here. So, the iteration matrix for H Gauss-Seidel will write down as a suffix Gauss-Seidel, that is equal to minus 1 upon 60 0 0 0 15 15 minus 3 21 minus 3 19. Now, if once I find the iteration matrix, for finding rate of convergence I want the largest eigenvalue of this matrix. So, let us form the eigenvalue for this matrix. Therefore, we can write down lambda I minus h or h minus lambda. I will use lambda I minus h because there is always a minus sign. So, I can absorb that minus sign over here. So, that will be equal to lambda. We take 1 by 60 inside. So, I will have 1 by 4 is 1 by 4 0 lambda, this is plus sign, therefore, this minus sign will be retained, therefore, this is minus 1 upon 20, 3 by 60 I will take it as 1 upon 20 and 21 upon 60, this minus sign is absorbed. So, 21 upon 60. So, I will have this, and this is minus 3 by 60, well 1 upon 20, and this is lambda minus 19 by 60. Now, the advantage when solving a 3 by 3 system for Gauss-Seidel will be, we know this column is always going to be lambda 0 0 0. So, the expansion will be very simple. So, let us expand it out. So, we will have lambda minus 1 by 20, lambda minus 19 by 60, and this is plus 63 by 60 square, that is equal to 0. So, let us simplify the interior, that is lambda squared minus this is 22 by 60 lambda, this is plus 19 by 60 into 20, 63 by 60 into 60. In almost all the cases these things do simplify a lot before we write it general form. So, this we can write as lambda 2 minus 22 by 60 into lambda, I multiply by this by 3, that is equal to 57 into 6 plus 63, that is 120 divided by 60 into 60. So, what I meant is when you have a factor outside this factor that is there, they always get cancelled to the minimum possible extent. Therefore, this I can write down the eigenvalues, therefore, lambda is equal to 0 and 60 lambda square minus 22 lambda, this is cancelled, that is equal to 2 is equal to 0. I have cancelled a 60 here. So, this is a 2 here. So, I will have a 60 lambda square minus 22 lambda plus this, or 30 lambda square minus lambda plus 1 is equal to 0. I find its eigenvalues this is simply 1 by 6 and 1 by 5, that is equal to, yes, 5 lambda plus 1 minus 1 into 6 lambda minus 1 is 0. So, lambda is equal to 1 by 5 and lambda is equal to 1 by 6. Therefore, the spectral radius of H Gauss Seidel is 1 by 5, the largest of these two, that is 0.2 or 1.5. Therefore, the rate of convergence is equal to minus of 0.2. This is approximately 0.6989. Therefore, this is how we can find the rate of convergence and then compare the rate of convergence of different methods like Gauss-Jacobi or successive relaxation or the Gauss Seidel methods we can do. We mentioned earlier that when we are solving the Gauss-Jacobi or the Gauss Seidel, the order that is given to us is very important. If you interchange the order of the system of equations, the eigenvalues will change because you are interchanging the rows. Therefore, the property of the convergence or divergence would completely be spoiled. Now, let me just show an example, a very trivial example. Let us take this example of 1 4 2 3 x 1 x 2 is equal to 5 5. Now, this is an artificial example in which I had taken the solution as 1 1, that is 5 and 5. So, this is a example. Let us solve this by Gauss-Jacobi. So, that is I want to see whether it is going to converge or not. So, let us write down H. H will be equal to minus D inverse of L plus U. So, minus, let us do D inverse immediately. In D is only 1 and 3. So, its inverse will be 1 1 by 3 0, L plus U 0 4 2 0. You remove the diagonal. So, what is left out is this. Let us multiply it out. This is 1 4 2 by 3 0. Now, let us find out the eigenvalues of this. So, lambda I minus h is equal to lambda minus h, that is lambda plus 1, this is 4, this is 2 by 3 lambda. Oh. No, I made a mistake here. This is a 0, this is 0, this is a 0. So, this is equal to lambda squared minus 8 by 3. Therefore, lambda is equal to plus minus 8 by 3. Therefore, spectral radius of H Gauss-Jacobi is root of 8 by 3 greater than 1. This diverges definitely. Therefore, if you apply the Gauss-Jacobi method to solve this system, it is always going to diverge. Now, let us do the same thing and see whether Gauss Seidel is going to converge. We have H is equal to minus D plus L inverse of U, minus D plus L is the lower triangular part 1 2 and 3, 1 2 3 0 inverse. The upper triangular part is simply containing 4 here, 0 0. Now, the value of the determinant is this is equal to 3. So, I will have this as 1 by 3, this is 3 0 1 minus 2. So, this is the opposite sign, there are -2, 3 and 1, and this is 0, 4, 0, 0. Therefore, I will have this as -1 by 3, 0 that is 0, 3 into 4 12, this gives you 0, this is -8. Now, let us find the eigenvalues of this. Therefore, I will have here lambda I minus h is equal to lambda, this is equal to 0. Therefore, this gives you 4 12 by 3, this is equal to 0, and this is equal to lambda minus 8 by 3. Therefore, this gives you lambda into lambda by 3. Therefore, lambda is equal to 0 and 8 by 3, and therefore, the spectral radius of Gauss Seidel is 8 by 3. Therefore, it diverges. It diverges much faster than Gauss-Jacobi. The Gauss-Jacobi spectral radius was only root of 8 by 3, whereas this is square of that number. Therefore, the Gauss Seidel is going to diverge much faster than the Gauss-Jacobi in this scheme. However, we mentioned that if the given system is diagonally dominant, then it would automatically imply norm is less than 1 and spectral radius less than 1. Therefore, in that case we do not have to bother about. For example, if I write a system like 4 1 1, let us say 2 minus 8 3 and 4 2 11. If I write down this particular system x 1 x 2 x 3 is equal to whatever the elements are, I can state that this system will converge for any method, Gauss Seidel, successive relaxation, or if it is of course make it a, if it is symmetric, other with the Gauss Seidel, all of them will converge because 4 is greater than 2, magnitude of -8, 8 is greater than 5, 11 is greater than 6. Therefore, this is a strictly diagonally dominant system. This is a strictly diagonally dominant system. This would imply that norm of norm of H is going to be less than 1, spectral radius of H is going to be strictly less than 1. Therefore, the convergence is guaranteed in this particular case. Therefore, this is always implies convergence. The only thing you would like to know is that what is the rate of convergence, otherwise we are guaranteed of convergence in a diagonally dominant system. Now, let us come to SOR. Now, we mentioned that in the SOR the H was minus d plus omega L inverse 1 minus omega into d minus omega u. We stated earlier that omega is the relaxation parameter and it lies between 0 and 2 in order that the SOR scheme converges. We also said that if it lies between 1 and 2, we call this as successive over relaxation. If it is lies between 0 and 1, we call this under relaxation, but we also mentioned we in practice nobody uses under relaxation unless there is some specific reason for using it, and omega is 1, it reduces to Gauss Seidel. Now, we also mentioned that it is necessary for us to find out an optimal value of omega such that the rate of convergence is the best. That means, we need to find omega optimum, optimal value of omega such that spectral radius of H is smallest. If I want the rate of convergence largest, spectral radius should be smaller, because it is spectral radius is less than 1. So, we are talking of rate of convergence of minus logarithm of spectral radius. So, if the spectral radius goes closer to 0, then the number is going to be log of that number is going to be very large. Therefore, such that rho of H is smallest. That means, it is finding the spectral radius and minimization of that with respect to lambda. That is what the problem is. I will not give the detailed analysis of this, but I will give the result. It connects the omega optimal connects with the iteration matrix of the Gauss-Jacobi and its spectral radius. We will denote mu by the spectral radius of H Gauss-Jacobi. That means, we can construct the Gauss-Jacobi, find its spectral radius, and that we call it as mu. Then omega optimum is given by this quantity 2 upon mu square 1 minus under root 1 minus mu square. Alternately, we can rationalize it also, bring this to the denominator, then this will cancel off and I will be left out with only 1 upon 1 plus under root of 1 minus mu square. So, either I use this particular form or use this particular form. Therefore, the omega optimum will be obtained by finding the spectral radius of the Gauss-Jacobi scheme, use that value and find this as omega optimum. And we always round off to the next digit, we do not use the normal rounding, this one round off to the next digit, round off to the next digit. I may just say the reason being that if you try to draw the graph of the spectral radius of the SOR with respect to lambda in this, to the left of this omega optimum, the slope of the graph is minus infinity. Therefore, there is a possibility that we may land into a non converging sequence. Therefore, we round it to the next digit, so that we are always safe in this case. Now, once this value is found, then the magnitude of lambda, that is equal to spectral radius of H SOR, is given by omega optimum minus 1. So, I find the omega optimum and then minus 1. We earlier said that omega lies between 1 and 2 for the SOR method. This will be my spectral radius of H SOR. Therefore, the finding of the omega optimum is not too difficult in the case of the wherever it is applicable. I need to find only the spectral radius of the Jacobi scheme, substitute it over it, find the omega optimum, and that omega optimum will give me the value that I should use it in the scheme SOR scheme that is available. If you remember, we have used the scheme as d plus omega L V k is equal to omega R k. So, we have used this error format for this SOR also. So, we could use this itself, and this is the value that we are going to substitute it over here and solve the particular problem. I think we will stop at this, we will do the example next time.